In this set of lecture notes, we're going to talk about 2D kinematics. So first of all, let me remind you what we learned about 1D kinematics. So first of all, we learned that kinematics is basically a description of motion without discussing reasons for that motion. So, for example, if a ball is thrown upward, we don't really discuss why or how it was thrown upward. We only discuss its subsequent motion. So we also learned three equations that we use for kinematics. So I'm going to write them like this. V equals V initial plus AT. X equals X initial plus VI t plus 1/2 AT squared. And V squared equals VI squared plus 2A times X minus X initial. So these are not new equations. Obviously, we've been using these equations. Now we're just going to apply them to more situations. So we've looked at each one of this in turn, and we know how to use them. We know where they're applicable. And one more reminder, we always say that kinematics is motion with constant acceleration. We also looked at free fall motion. Now, in order to get equations for free fall, all we're doing is just substituting negative g in place of acceleration. So these are not new equations again. These are literally the same equations where I'm substituting y instead of x, and then writing this out with negative g instead of acceleration. So all exactly identical other than those two little changes. So this was all 1D stuff. So we talked about specifically we talked about general kinematics equations, and we talked about specifically applying those equations to free fall motion. Now we're going to make things a little bit more general even. So we're going to talk about 2D kinematics. And you hopefully kind of see where I'm going with this. In two-dimensional kinematics, we're going to use all of the ideas that we used for 1D kinematics, except now we're going to use them for x and y dimension. The most important thing about two-dimensional motion, even if it wasn't kinematics, if it was anything really related to two dimensions, the most important thing is that x and y are treated separately and independently. This statement is so important that I'm going to box it, even though it's not really an equation. So x and y are treated separately and independently. So basically what that means is whatever is going on in the x direction has no influence on the y direction. And vice versa. Whatever happens in the y direction has no influence on the x direction. In principle, I could even take that statement and extend it to 3D. So then I would say x, y, and z are treated separately and independently. So whatever happens in one of those dimensions has no influence whatsoever on the other two. But for the time being, we're going to stick with x and y only. We're not going to worry about z just yet. Now, because we're talking about kinematics, we obviously also need to think about acceleration. We're going to take that idea of acceleration being constant and extend it to writing ax is constant and ay is constant. Right? Since we're considering two dimensions, we now have to talk about two different accelerations. In fact, everything that we discuss is going to be, well, in two dimensions. So we're going to have basically a set of equations describing x and a set of equations describing y. So let me write those. Now these equations should look very familiar to you. In fact, all I'm doing is just rewriting these equations that I wrote above, literally. And the only difference that I'm gonna have here is this. Let me finish writing this first. So these are my x equations, right? Let me label these guys. X direction. Okay. So the only difference here is that each velocity and each acceleration is specifically in the x direction. So each of these pieces only contributes to x. And of course, position x is x, right? Then I'm going to do the same thing for y. Keep things consistent here. Okay. So notice what I'm going to do. I'm not even going to worry about free fall. I'm only going to literally write these general equations as applied to y component. So at first glance, you really shouldn't even be able to tell any differences, right? Other than I literally replaced x with y. And that's exactly what it is. So just because we're talking about 2 dimensions doesn't mean that we have to treat x and y any different. So the only place where the differences comes in is in me labeling all of this components of velocity and acceleration very carefully in terms of x and y, right? So now if you compare these equations, the set of equations for x is identical to the set of equations for y, with the exception of all of those labels, right? So if we're talking about velocity in the x direction, that's distinctly different from velocity in the y direction. If we're talking about acceleration in the x direction, that's distinctly different from acceleration in the y direction. Also, I just now mentioned the word component, so let me remind you. If we have, for example, a velocity vector, well, any vector for that matter, but now we're applying it to kinematics, so I'm going to call it velocity vector. We can find its x and y components, right? We can draw it like this. Let me label theta here. We can draw it like this, kind of like a rectangle type thing, right? Or we can also label it like this, using a triangle. Either way, you guys already know how to find these components, right? We've talked about them in the previous set of lecture notes. So all the vector math is going to stay exactly the same as what we discussed before. The only difference is that I'm no longer talking about any random vectors. I'm talking about specifically a velocity vector. Okay? So I'm going to calculate the x component of this velocity vector by using v cosine theta. And I'm going to calculate y component of the velocity vector by using v sine theta. Now, what should I box here? Actually, really nothing. Because we've seen all of this before. We've seen vectors. We've seen kinematics. Again, I keep emphasizing this. This is not any different from what we have already learned, right? So all we're doing is just clarifying which velocity and which acceleration we're talking about. I guess I should also do the same thing for acceleration. If we had an acceleration vector, right, then I could also find components of acceleration vector like this or like this. Right, so again, this is not any different from working with any generic random vector. This is identical to everything that we already did with vector stuff. That's why I'm not even going to box it, because I don't want you to think of this as something different. All we're doing is taking velocity vector and acceleration vector and resolving each one into components, keeping in mind that what we need to do is treat x and y separately and independently. Now, there are a lot of different two-dimensional motions. So, for example, I can do something like this, general 2D motion. So, for example, if I had xy plane, right, and I can just draw a random path of an object through an xy plane, I can figure out what's going on with velocity and acceleration. We'll actually talk a little bit about acceleration in the next set of lecture notes, but I just want to make it a point here. Velocity vector is always tangent to the trajectory. Doesn't matter if it's 1D, 2D, 3D motion, doesn't matter. So these are my velocity vectors. At different points, of course, right? So velocity, the way that I'm drawing it here, velocity is not constant by any means, but it doesn't matter if it is or not. So let me write that too. Velocity vector is always tangent to the path, or you can also say trajectory. Okay, and this is true in 1D, 2D, or 3D motion. Okay, so whatever the shape of the path is, you can always draw a velocity vector at every point by drawing a tangent to that path. So this is kind of generic motion. There are two more specific kinds of motion that we're going to describe: projectile motion and circular motion. Okay, so we have to consider both of the subcategories of the general motion. And of course, there is any number of different shapes of path, different motions, whatever you want to call it. All of those, doesn't matter what's going on exactly, all of that is going to be governed by these principles. Most important one of which is that x and y are always treated separately and independently. Motion would be simultaneous in x and y. So all of these equations where you see t, you're going to use the same t for x and y. But you're still going to do these calculations separately and independently. Okay, I'm going to introduce projectile motion, and then we'll talk more about it in more detail in the next set of lecture notes. So projectile motion is a special subcategory of two-dimensional motion where motion is 2D, but the only force acting on whatever object is force of gravity only. So right away, you hear the term force of gravity, especially when I'm telling you that it's the only force. Again, considering we haven't really discussed any other forces just yet. But this would tell you that we have free fall situation. Okay, so 2D motion, but free fall. Okay, so the shape or the path doesn't matter as long as you recognize that the word free fall represents only downward acceleration. So what this boils down to is acceleration in the x direction is 0, right? So constant equals 0. And acceleration in the y direction is equal to negative g. So I'm going to take all of those equations that I wrote above, rewrite them again, and then make some simplifications. So notice how I'm going to be very careful here putting all of those subscripts again. And again, these are not new equations. I'm going to probably repeat that a few more times. All I'm doing is just rewriting them several times to make certain points. Okay, so here are my x equations, right? Okay, I might as well just write y equations right away. Okay, so we have free fall in the y direction. Okay, so here are my x and y directions. I should label them too, x and y. Now, y direction, since it's free fall, technically it's already as simple as it gets, right? So that's all there is to it. Those are our equations for y. For x, we can make simplifications. Remember how we said ax is equal to 0? So let me get rid of all of the terms that have ax in them. And then what do we have? Well, the first equations just turn into vx equals vix. That's really not much of an equation. The last of these three turns into vx squared equals vix squared. That basically means the same thing, and again, it's not much of an equation. So basically what this means is that velocity in the x direction is constant. And you should be able to relate that to the fact that acceleration in the x direction is 0, right? So if the object is not accelerating in the x direction, that means velocity in the x direction is constant. So these two quote-unquote equations, they're not really equations, right? So if I'm specifically talking about projectile motion, that's the key. We can actually get rid of those two equations in the x direction because they really don't tell us anything new other than vx is constant. But we already know that, right? So those two are unnecessary. Now, the second equation here, I'm going to rewrite as x equals x initial plus vx t, right? So if I already know that velocity in the x direction is constant, I might as well just call it vx as opposed to vix. And this equation we've seen before, right? So I'm not going to box it, but I'll circle it just to bring your attention to it. We had this equation before when we talked about uniform motion. Uniform motion in x direction specifically, right? This was one of the very first lectures that we had where we wrote distance equals rate times time. So that's basically that, right? So that distance equals rate times time, that's kind of third grade stuff, so we don't really need it. But that was the meaning of it, right? Now, when we say acceleration in the x direction equals 0, when we say vx is constant, or when we say that we have uniform motion in the x direction, there is also no new information there. All three of those quantities are exactly analogous, or excuse me, all three of those statements are exactly analogous to each other. So you can use any one of these three statements and get the point across equally well. Okay, so we have uniform motion in the x direction, and we have free fall in the y direction. And that's literally all there is to it for projectile motion. So the idea of, well, any two-dimensional motion, but specifically projectile motion, is that we're going to treat x and y separately. For projectile motion, we'll have uniform motion in the x direction and free fall in the y direction. And that's literally, that's it. So we'll do a few examples in the next set of lecture notes, and also kind of develop this idea a little bit more. I'll show you different things that you can do with projectile motion, but I'm just going to draw this picture really quickly just so that you have a starting point. So something like this, like launching a ball at an angle. Right? This would be an example of projectile motion. Something like this. Right? So see how I'm launching a ball at an angle with a certain velocity, right? So that by itself, the fact that I'm launching it at an angle, that should give you a clue to the fact that you would have to use either generic 2D equations or more specific projectile motion equations. Chances are, if you have something of that sort, so you have a parabolic path, right? So it's part of a parabola. So if you have parabolic path, it's pretty much guaranteed to be projectile motion.